In this week's lab, we're going to learn how we use records of stream flow to determine the expected discharge of a 100-year flood. That flood that has a 1% chance of being seen or in any given year. Again, it's not a prediction of when flooding occurs, but rather what is the probability of seeing a flood of a given size. The graph that you're looking at shows peak annual discharges for the Willamette River at the Albany measuring station. What's plotted here is the highest flow or discharge for each year, and it's just simply plotted as a time series. One of the things that you'll immediately notice about this graph is that there's been a change in the size of the peak annual discharges. Back in this period, say before the mid-1960s, we see larger peak annual discharges, and then the peak annual discharges abruptly drop after about the mid-1960s. This is reflecting the influence of dam construction on the upper Willamette and its tributaries. The dams serve a variety of purposes, but one of those purposes is to hold back water during periods of high flow, thereby reducing the peak flow events. In other words, reducing the size of floods on the lower river. The dams provide a storage capacity to hold water back upstream and then release it more slowly over time, thereby reducing the peak flow. Because there's an obvious change in the size of the peak annual discharges, the frequency of discharges of different sizes has obviously changed over the time period of record. Larger flows were more frequent back in the earlier time period, and then become less frequent as we move to the present. So for this reason, we're going to do the same analysis twice for the Willamette River at Albany. I've picked a 10-year period here, 1950 to 1960, and another period of equal length, 1970-1980. As a result of the analysis, we'll see how the probability of seeing discharges of different sizes and the magnitude of those discharges has changed with time as a result of changes in the watershed. Dam construction is an example of one change, but land use changes and their effect on runoff, potential climate changes, and so forth can all affect the size of discharges and frequency or probability of seeing a discharge of different sizes. This table shows the peak annual discharges for specific years. Again, I'm going to do the analysis twice, once for each of these time periods, so that we can see how the results change, how the probability of floods of different sizes has changed as a result of dam construction on the Willamette River. The first step in this kind of analysis is to rank the peak annual discharges, from 1 being the largest, 2 being the second largest, all the way down to n, where n is the number of years in the data set. Each of these data sets has 11 years, and so the smallest flood is going to have a rank of 11. Here I've gone through and ranked the discharges in each data set by size. Largest discharge is ranked number 1 in each data set. Second largest discharge is ranked number 2 in each data set, and so forth, all the way down to the smallest discharge, which is ranked 11th, because each of these data sets covers 11 years. The next step is to calculate the recurrence interval for each rank. Recurrence interval is an expression of the frequency, how often, on average, we should expect to see a flood of that size, given the range of discharges we have in each data set. Recurrence interval is calculated simply from the rank of that discharge. The formula for calculating each recurrence interval is given here. N is the number of years in the data set. In this case, N always equals 11 because we have 11 years of data in each set. M is the rank of a particular discharge. Largest discharge is equal to 1. The the smallest discharge is equal to n, or has a rank of n, and in our case being 11 because we have 11 years of data in each set. For example, the discharge rank number 1 has a recurrence interval equal to 11 plus 1 divided by 1. 11 is n, 1 is m, or rank, and n, number of years in the data set. So our largest flood, rank equals 1, has a recurrence interval of 12 years in each data set. When we actually plot our data, we're going to be plotting recurrence interval versus discharge. Recurrence interval is going to be the x-axis. Discharge is going to be the y-axis. And as a result, we're actually going to get two different graphs. As you can see, there's a different discharge associated with each recurrence interval because the discharges in the data sets are different. The flood rank number 2 is going to have a recurrence interval of 6 years. Again, 11 is n, 2 is the rank, so 11 plus 1 divided by 2 gives us 6 years. The second largest flood has a recurrence interval of 6 years with n, number of years of data, equaling 11. The discharge that's ranked number 3 has a recurrence interval of 4 years in each data set, again because the number of years of data is 11 in both cases. And so on. Calculate recurrence interval for each rank using n plus 1 divided by m. N is the number of years of data, or the number of years in the data set, and m is the rank of that flood or discharge. The next step is make one graph for each data set. In other words, make a separate graph for each data set. Your recurrence intervals are similar, but the discharges associated with each of those recurrence intervals changes. Recurrence interval is going to be on the x-axis. Discharge is going to be on the y-axis. In other words, x equals the recurrence interval, y equals the discharge for that recurrence interval. Now these graphs may look a little bit different than what you've seen before because the x-axis is a log scale. By that I mean it's powers of 10. The y-axis is a linear scale, which is the normal scale that you've seen many times before. When you're making your graphs, you're going to have to choose a scale for your y-axis based on the range of discharges you see in your data set. For example, the Willamette River data set covering the years 1950-1960 has discharges ranging from 174,000 CFS, cubic feet per second, to 62,000 cubic feet per second. So we're going to scale our y-axis from about 60,000 CFS to about 180,000 CFS. But again, we don't want our data to fill any more than about half of the y-axis, and you'll see why in a minute. Ultimately, what we're going to do is after plotting our data, we're going to extend the relationship that we observe between recurrence interval and discharge out to the 100-year recurrence interval. We need to leave ourselves room to do that because the discharge for the 100-year recurrence interval is likely to be much larger than the range of discharges in our data set. So if you don't leave yourself room on your y-axis to extend your line to the 100-year discharge, it's going to go off the top of the page, and you're going to have to redo your graph from the beginning. Once we've got our data points plotted, 11 data points for each graph, we're going to draw a line through that data set. We're not going to connect the dots, but rather we're going to draw one straight line, a best fit line, and draw it in such a way that there's an equal number of points above and below that line. The way a computer would draw a best fit line is it would calculate the total distances of points above and below the line. In other words, the sum of the distances above the line would be equal to the sum of the distances of points below the line. We're then going to extend our line, one single straight line, all the way out to the 100-year recurrence interval. So here's the graph we're going to plot. X-axis is recurrence interval, units of years. Y-axis is discharge, units of cubic feet per second. Let's plot the Willamette River 1950 to 1960 data set first. Range of values in that set go from a high of about 174,000 cubic feet per second to a low of about 62,000 cubic feet per second. As a result, I've scaled my y-axis from 60 to 180,000 CFS to incorporate the range of data in that set. And I've scaled the y-axis in such a way that I'm not filling more than about half of the y-axis, leaving myself room to extend my line all the way out to the 100-year discharge without going off the top of the page. So the flood with recurrence interval 12 in the 1950 to 1960 data set has a discharge of 174,000 cubic feet per second. So it's going to plot about right there. The flood with a recurrence interval of 6 years has a discharge of 155,000 CFS, plotting about right there. The flood ranked 3, recurrence interval of 4, its discharge is 146,000 CFS, plotting around there, and so on. Flood ranked 4, recurrence interval equals 3 years, discharge 112,000 CFS. Flood ranked 5, recurrence interval of 2.4, 2.1, 2.2, 2.3, 2.4, has a recurrence interval of 106,000 CFS. Recurrence interval 2 years, discharge 99,000 CFS. Recurrence interval 1.7 years, discharge 82,000 CFS. Recurrence interval 1.5, 1, 2, 3, 4, 5, that's 1.5. Its recurrence interval, or its discharge, 80,000 CFS. Recurrence interval 1.3, discharge 77,000 CFS. Recurrence interval 1.2, discharge 63,000 CFS. Recurrence interval 1.1, discharge 62,000 CFS. We've got our 11 data points plotted. I'm now going to lay a ruler, adjust the fit of my line, and draw a line again that doesn't necessarily pass through all the points, but rather results in an equal number of points above and below the line. And we're going to draw that line all the way out to the 100-year recurrence interval. What's the discharge associated with the 100-year recurrence interval? 210, 240, 270. That would be 300,000 CFS. We're sitting at about 285,000 cubic feet per second. In other words, the 100-year flood, the flood with a recurrence interval of 100 years, or 1% chance of occurring in any given year, has an expected discharge of 285,000 cubic feet per second. You would do the same thing for each of the data sets. Because the range of discharges is different in each data set, we're going to get a different expected discharge for the 100-year flood. Here we've plotted the data for the second data set, Willamette River 1970 to 1980. We're now going to draw a best fit straight line like we did before and find out what the expected discharge is for a 100-year flood. Notice that one of the data points looks like an outlier. That data point for the 1.1 recurrence interval is quite a bit lower than anything else. So in drawing our best fit line, we're going to largely ignore the data point that we've identified as an outlier. We're going to position our line in such a way that we have an equal number of points above and below the line, and we're going to draw it all the way out to the 100-year recurrence interval, and then read off the expected discharge. Expected discharge is about 165,000 cubic feet per second for the 100-year recurrence interval. It's quite a bit different than what we found in the previous data set, reflecting what we expected to see from the graph that we started off with. We saw that peak discharges have decreased after the mid-1960s with the flood control capacity provided by the completion of dams in the upper part of the Willamette watershed. So what does all this mean? What we're getting, again, is not a prediction of when a flood is going to occur, but rather we're learning what to expect in terms of the size of a given flood. What we've learned is the expected discharge for a flood of the 100-year recurrence interval. We could get the expected discharge for a flood of any recurrence interval we might be interested in. But typically the 100-year recurrence interval is what's used because that serves as the legal definition of areas that are at risk of flooding. Now, 100-year flood does not mean that a flood of that size would occur once every 100 years. Instead, what it means, or it's better interpreted as a probability, a chance. Probability is just the reciprocal of the recurrence interval. A 100-year flood has a 1% chance of occurring in any given year. That might not sound like much, but risk is cumulative. Each year, you have a 1% chance of seeing a discharge of that size we expect based on the analysis we just did. Let's say you take out a 30-year mortgage to buy a house. Within the lifespan of your mortgage, there then becomes a 30% chance of seeing at least one 100-year flood. In other words, 1% times 30 years, we have a 30% chance of seeing at least one 100-year flood within the life of that mortgage. Now it's starting to sound a bit riskier. This is why banks will not lend you the money to buy that house unless you also carry flood insurance on that house, because banks are not willing to take that risk. You're free to take that risk, but the bank is not willing to do so without the flood insurance protection. So in mapping out areas that are at risk of flooding, we would take the discharge that we expect to see for a 100-year flood, as given by the analysis we just did, convert that to a height or elevation, and then map out that elevation on a topographic map, showing the area that would be flooded when the river flow is that high. If your property maps within the area flooded at the 100-year discharge, you live in that river's legal floodplain. And if you have a mortgage, you'll be required to pay flood insurance premiums as a condition of that mortgage.